In the early 19th century, Norwegian chemists Maximilian Goldberg and Peter Waj made an important proposition that improved our understanding of the equilibrium constant in reversible reactions. They stated the law of mass action, which posits that the rate of a chemical reaction is directly proportional to the active masses of the reactants. This basically means that the rate at which a reaction occurs depends on the amount of reactants that are converted to products. So the more reactants that are converted to products, the faster the reaction. Now, this is quite easy to spot for a non-reversible reaction because for such reactions, the reactants and products are well defined. For example, if we dissolve calcium trioxocarbonate 4 in hydrochloric acid, we know that calcium trioxocarbonate 4 and hydrochloric acid are the reactants, which will eventually form products. On the other hand, for reversible reactions, since they proceed in both forward and backward directions, there is neither a clear reactant nor a clear product. All the species in a reversible reaction are both potential reactants and products. This means that the rate of reaction talked about in the law put up by Goldberg and Waj will be a function of the active masses of the reactants in the forward reaction and the reactants in the backward reaction. Also, it is important to note that since the masses of reactants and products of the species in a reversible reaction may not be easily measured, we represent the active masses of aqueous solutions as their concentrations in mole per dm cubed raised to the power of the number of moles of that particular reactant. For gaseous species, we represent the active masses as the pressure of the gases raised to the power of the number of moles of that particular reactant. While for solid and liquid species, we ignore their active masses or represent it as 1. Knowing all these, we can now write the equation for the equilibrium constant of a reversible reaction. Let's try to give the equilibrium constant for the reaction represented by this equation. In this reaction, D, E, and F represent the number of moles of A, B, and C respectively. To write the equilibrium equation for this reaction, we will first write the rate of the forward reaction, which has A and B as its reactants. The rate of the forward reaction will be equal to the equilibrium constant of the forward reaction multiplied by the concentration of A raised to the power of D times the concentration of B raised to the power of E. Also, we will give the rate of the backward reaction, which has C as its reactant. The rate of the backward reaction is equal to the equilibrium constant of the backward reaction multiplied by the concentration of C raised to the power of F. Now that we have the equation of both the forward and backward reactions, we can get the equilibrium constant simply by recalling that at equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. This means that at equilibrium, we have this equation. From this, the equilibrium constant Kc of this reversible reaction can be gotten to be the ratio of the equilibrium constant of the forward reaction to the equilibrium constant of the backward reaction, which is represented by this equation. One last thing that I want you to note is that I have intentionally used square brackets to represent concentration. A curly bracket or round parentheses are unacceptable and should not be used to represent concentration. In summary, the whole idea of this lesson is that we can obtain the equilibrium constant of a reversible reaction by dividing the active masses of the products by the active masses of the reactants. I know this appears a bit difficult, but give it time. In a future lesson, we will find the equilibrium constant of actual reactions, and you'll get to understand this better. I hope to see you then.